for that. Okay, the lecture starts with some historical facts, and the title of the course is kind of Elements or Elementary Elements of Topological Vortex Dynamics. I give you very briefly the plan of these lectures. Today, you will understand this maybe in the following lectures, but for today, I will focus, starting from history, on some basic facts of vortex dynamics, quickly, relying also on the lectures of Luis Vega, and I will consider aspects of vortex dynamics in a multiply connected domain. So imagine that you have a region of space where there is an empty tube, and you guess what I mean. The empty tube, really empty, it will be then regarded as a vortex tube later on. Evidently, I will talk about vortex filaments and aspects like that, but that's why the first part has this title, Kelvin's Topological Vortex Dynamics. Once we do this, we will have a number of information that we will use in the course of these lectures, especially towards the end. Tomorrow, maybe today, we'll start talking about helicity, but certainly I will focus on helicity and its topological interpretation in terms of linking numbers. Then there is a gap day on Wednesday, and then on Thursday, my lecture will be indeed on the Biosavar desingularization, which relies on LIA, on the localizing or the binormal flow that Luis introduced this morning. And I'll tell you something about what we can say about vortex knots. Then Friday, we will have 2 lectures, and because of that, I will try to be light on the very last one. The first part is dedicated to reconnection, of course, vortex reconnection, and change of topology. And then the very last lecture in the afternoon, you know, there is a reconnection of vortex filaments, and so you can think of this pattern of decay of complex structure into small scale vortex structures. And so is what I want to focus on is on the topological cascade of vortex structures, and then mentioning something, not very much, but on our recent work on knot polynomials. That's the plan. Now, consistently with this, I like to think of, you know, for school, it's very good to have a sense of history of science. So here we have more or less 1860s, and then a jump more or less of 100 years to get to helicity. I will talk about that. 1960s, more or less. And then these desingularization techniques applied to Biosavar, etc., are from the 70s, 1970s, and then focus on reconnection and change of topology. Well, as Alain Poumire probably is here, I think 1990s, a bit earlier than that, 80s. And then this thing is recent. So let's say 2020, 2010, something like this. Okay? So you have an idea of the time and focus on things. So in essence, all this program formulated not in these particular words, of course, was already in the mind of Kelvin. And I tell you something about that. And in the notes you will have some pictures here. I prefer not to interrupt my presentation with slides, etc. But you will have reproduction of some very interesting results and ideas of Kelvin. So let's start with Kelvin. Kelvin relied on work of his contemporaries, and these two German guys. One, of course, you can guess it, Helmholtz. And the other one, Riemann. Apart from Euler, Riemann can be considered the originator of topology, as said, apart from Euler, of course, Euler as well. Maybe Euler is more related to graph theory nowadays. Helmholtz, you know, because has been so influential in many, many fields, and in vortex dynamics as well. So let me start from scratch, so to speak, and I'll tell you something about this. Before doing this, however, I'll tell you some words about these Kelvin's project. So Kelvin could be regarded as ante litteram string theorist of the time, because he wanted to develop a theory that was accomplishing all was known at the time in all fields. So, you know, you're accustomed to think, okay, how to encapsulate gravitation into classical physics or quantum field theory. Well, exactly these kind of things. He wanted to have, of course, gravity. He wanted to have electricity and magnetism. He wanted to have everything. And what was unhappy about was this, let's say, Greek. Of course, we can say exactly who contributed to, but this Lucretian idea that atoms were at the foundation of everything, of matter. He wanted to give a reason for that. And he couldn't find the fundamental reason for that until he read the English translation of Helmholtz's paper. I will quote the conservation laws of Helmholtz very quickly. Essentially, Helmholtz said that in an ideal fluid, vortex filaments, let's say, vortex tubes, etc., were conserved and topologically conserved, I mean, and also provided a quantitative measure for their strength being conserved. What we may call, you know, according to your taste, through Stokes' theorem, Kelvin's circulation theorem. So circulation was conserved, etc. But the fact that these objects were permanent once created, permanent in an ideal fluid, gave exactly the idea that Kelvin used, thinking of these vortices as very tiny microscopic atoms. Why he wanted to do that? Well, because he had a problem. The problem was that from chemists, he knew that energy was appearing, at least through the spectral analysis of chemical elements, energy was appearing as discrete packets. And so you had to find a way to quantize energy. And the idea he had was just very, very genial. He thought, okay, I have these vortices, and Helmholtz tells me that these quantities are conserved topologically and in terms of fluxes, etc. How can I get this discrete energy spectrum? And the solution was, well, if I think of these vortex filaments in the shape of knots and links, if I think of a knot, the knot has a topology and measured, let's say, in a very simple way by crossing number, minimum number of crossings of the knot type. And so there is a trefoil knot and the 4-crossing knot and the 5-crossing knot. And if you assume that these vortices cannot recombine one strand with another, if you assume that they stay like knot type in an ideal fluid without any reconnection, then of course whatever the energy associated with the knot is kind of discretized by the topology. So he was very enthusiastic about this modern idea, which is still around in high energy physics, let's say. And so he asked his good friend Tate to tabulate knots, and he just set a program, an amazingly ambitious program. He said, okay, I work on the knot dynamics, and you tabulate knots. And so by putting together this information, we can prescribe the energy for each knotted or linked vortex in ether. Ether is a Greek word, comes from Greek, and means simply an ideal fluid and hypothetical fluid. So it doesn't exist, or it was proven that it didn't exist. But he imagined that this hypothetical fluid, ideal fluid, was at the level of, say, atom. Okay, at a microscopic level, then you have particles there, and the particles, the fundamental particle, of course, had to be the vortex ring. And what about a ring linked with another ring? Then would form a link that has the name of a Hopf link. Suppose that these are my center line of the vortices, then this link would stay there forever. And we may think this, of course, is my invitation to you to be very generous with your mind. Well, you may think that this is hydrogen, H2, and then you have oxygen, and then you have all the other chemical elements. And to get all these other chemical elements, of course, you had to increase topology. For example, well, you can put another one here. Why not? So imagine that you have a link like this, okay, and then so on and so forth. Of course, knots. And this is a trefoil knot that we saw in the beautiful experiment by William Irvine, and the trefoil knot was his starting place, as well as vortex rings. He asked Tate to produce vortex rings, and then they went on and on for almost 2 years to shoot rings one against the other, trying to create a trefoil knot. So that's why the experiment with William Irvine was so scientifically and media-wise of great impact, because, of course, nobody realized the trefoil knot before, especially in water. They tried in air by shooting smoke rings, etc., etc., etc. Okay, so this is the idea that led Kelvin to consider topology. And he relied on Helmholtz's work, conservation laws of Helmholtz. And there is a little footnote of Helmholtz on Riemann. You know, this is a paper 1858, and this is the paper by Riemann. Yes, is 1 year earlier, not quite, 1 month earlier, December, and this is January. And the two were talking together in Göttingen about this idea of Well, if you have vorticity, the curl of velocity, equals 0 someplace and non-zero in another place, how these two regions talk to each other. You know, the vortical region doesn't talk to the other one because the assumption was that it's an ideal fluid, no viscosity at all. So how they could ever get in touch one another. Okay, so this is the little history. I spent quite some time to investigate this, and I have to tell you that there are lots of not quite good representation of this by historians. Sometimes they are a little bit superficial. But I went through the handwritten notes of Kelvin at the time in Cambridge Library and Glasgow. And it was a very, very useful exercise. So I decided, in the view of the program I want to present you, with you, to repeat one of the exercises of Kelvin. Exactly the same. And there is a reason that is not historical. The reason is I use Kelvin's work to show you, maybe tomorrow, you have to be patient, something that has been done and published 2 years ago, 3 years ago, and it relies, in a sense, on zero. You know, it starts from scratch, but is basically very, very strictly connected with Kelvin's work that I'm going to show you. And this is a quite modern work, what he did in 1870s. You know, at the time, it's like when we read some of the modern work in high-energy physics and we don't understand the word, because we don't catch that world. And that world is the world that Kelvin had in mind and was very, very difficult to be accepted by others. But, so it's not a joke, but Maxwell was taken very much by this, and he decided to introduce lots of notions about topology in his book. Yes, Electricity and Magnetism. Volume 1. He made, can we say a mistake? Yeah, why not? He made a mistake, and now listen. He made this mistake. He called this introductory chapter preface. Who reads prefaces? Nobody. Nobody. So go to volume 1 and read the preface, and you will see the best introduction, how to say, applied maths introduction to topology. But of course, it was totally incomprehensible for people. He was talking about tunnels in the fluid, and the problem that potential was ill-defined in the sense that it was multi-valued, and that was known from Riemann. And then he insisted how to make this strange Swiss cheese simply connected. Can you imagine at that time? Even now. Why they care about these things? Who cares about these things? So maybe he was clever. He called it preface. And he went on. Okay, so, well, I don't want to spend too much time on basics, but I just like to remind you, because I know my business. I know I've been a student myself, and sometimes, so forgive me if I'm so simple. But first of all, remember, there is a Helmholtz, what is called now Helmholtz, maybe is not Helmholtz, Helmholtz decomposition theorem, in modern words. So we have a fluid flow, and I will be just one line. And you have to imagine that we have a velocity at a point x and time t, and this velocity field is, you may think, if you take a point and you kind of tailor expansion nearby this point to a neighboring point, then you have what already Lagrange noticed, that these can be written in terms of linear superposition of three fields. Let me call it, for simplicity, a kind of rigid motion translation field plus something that you can call it a deformation of the volume element, and thirdly, a field that is due to the presence of a curl of rotation. Okay? This has been expanded further by Hodge, etc., etc. It's a beautiful piece of mathematics. So I won't talk about this. I assume UT means that there is a flow that is flowing in this room, and there is a vortex, and the vortex is, if it were, like Professor Vega said, if it were rectilinear, it wouldn't move at all, but it would be transported by the flow. So UT, okay? Oh, okay, I say, all right, I don't care about this UT. I rescale everything. And then this UD. Well, UD, okay, that's quite interesting, is due to the deformation of the volume of the fluid volume element. A deformation, maybe the volume stays the same, but is squeezed, is deformed. So I won't care about this at the moment, and of course, because of the aim is on vortex filament dynamics, I'll care about this UR, and this is the velocity that we all care about, is what we may call it a self-induced velocity, a velocity that the vortex itself creates because of the presence of vorticity. Right. Okay. So this is the point. So I want to say, okay, how can I compute this velocity? And you already know the answer, and is through your basic maths to get to Biosavar, right? So you have basically, was mentioned this morning, you have, let's see if I want to be consistent a little bit with this. We assume, because of this, we assume that the UR is divergence free, and then we assume that, of course, we have a curl of UR, and we call it vorticity, omega. And then we explain UR, we express, UR in terms of a potential, curl of the vector potential associated with this rotation, and then, of course, as Luis said, you take the curl of the curl, and you expand it. So you get AR. And AR is the potential associated with the velocity in this particular setting. Now, of course, we use potentials, right? Physicists don't like very much potentials, except in the last 50 years, 30 years. Maybe some of you know Aharonov bomb experiment. Anyway, I ran many years ago I had lunch with Sergei Novikov, and that was more or less 2000. And I said, great topologist. And I said, what do you think about physics and topology? He's settled, Renzo. Don't worry, he's settled. He was very typically Russian and style. And what he meant was that 10 years earlier, in the last 10 years, so in the 90s, finally, it was done before, but finally, the idea that topology had an impact on physics was proven, in particular by a group by Tonomura et al. But as I said, there was already kind of proved earlier by others. Anyway, potentials were not considered important, and even now, many physicists, you know why? I mean, it's perfectly reasonable. Physicists, they measure a force. They don't care the grad of the potential, because there is no way to measure the potential except by this Aharonov bomb experiment to show that the topology of the ambient space has a role in the physics. So, very often you read is a mathematical artifact for physical reasoning. So that's one, AR. Okay, so this AR, you just go through, as was mentioned, the what we call the Poisson equation for vorticity, and this is basically this. And so you get to AR by Green's potential theory, and then you get the standard expression, 1 over 4 pi in the volume of vorticity. And let me stress that this x star is the source of vorticity, and x is the induction point. So this AR should be an AR of the induction point, okay? All right, I'll do that. Here? You like a plus? Oh, I'm sorry. Yes, I'm for some reason I'm used to put the nabla squared. All right. Okay, so you work on this right there, and you get your UR as we know it. I skip just a few passages just to have this form 1 over 4 pi omega of x star, and then we have an x minus x star as usual. These by now is very, very classical stuff. When I was young, I learned to pay attention to some factors, and that was confirmed by my great teachers I had in life. And this 4 pi, you know, I'm tempted, I'm sorry, I'm jumping on time to time, but I'm tempted to do this. Please consider R as x minus x star, and then R hat, unit vector, as x minus x star divided by x minus x star, you see. And then we can write this as 1 over 4 pi. Well, you read it. We have an omega of x star. And then this x minus x star goes to r hat. So we have an r hat somewhere here. And then we are left with an r squared, right? Okay, and I don't like a 4 pi outside. So can we regard this as a 4 pi r squared? It's quite nice, actually, because, you know, if you think of a surface as a sphere and of radius r, there is a beautiful way to interpret this in terms of a solid angle. I'm anticipating things, right? But this is one way to look at it, at Biosavar. We will get back to that because it's very interesting, very interesting. And Gauss relied on that very much. And Maxwell, of course, relied on that very much. All right, so this is what is well known, Biosavar law. Is a self-induction because omega given at a particular point in space induces the velocity ur at a point x in space. Notice that this is the domain of vorticity is a global integral. Global integral, in a sense, is a global geometric integral. And so when we do some approximations here, we have to be very careful because we are going to break this global property. And because it has global properties, it's reminiscent, at least superficially, of topology. Okay, so we can think of this in this fashion. Right, so this is just a quick remark on Biosavar and how it's derived. And then, well, conservation laws. Conservation, well, we have a number of conservation laws in ideal. So Euler equation, okay, Euler's equation. Energy. You should be able to prove it straight away this evening. Go home and kinetic energy, half of the integral of u squared. You plug in d dt of that quantity should be 0. So you imagine this integral is in a material bounded by a material surface, so you can get inside with your derivative with respect to time, and so you have u squared, derivative of u squared is a 2 u du, and by du you plug the Euler's equation that you should know. Okay, the Euler's equation, of course, involve a grad of pressure, and so you should be able to prove yourself that let me say E, kinetic energy is conserved. Okay, then we have this famous ingredient that we call Kelvin Circulation theorem. The ingredient is that many people refer to it as a Stokes theorem, and the funny bit is that Stokes gave the problem of the student, and then he lost track of the student. And when he realized that the proof of that quantity was rigorous, so to speak, he stand up the checking, then he already lost the track of his student. So we call it the Stokes theorem, and it is due to a student of Stokes in Cambridge. So we call it, well, say gamma. Maybe sometimes I'll switch to phi because of the use of fluxes in other contexts. So this is circulation. Circulation. And you know what is circulation, right? Okay. Then we have other conserved quantities. Here we are still, I mentioned Stokes, right? So we are 1870s, more or less. Then we have linear momentum and angular momentum, and these are also conserved. A linear momentum and angular momentum. More or less, we are in 1950. And then came by a French mathematician, Moreau, in Montpellier. In 1961, he could prove that another quantity that we call it H, helicity, or better, kinetic helicity, should say. Kinetic helicity is also conserved under Euler flows. There is a sister other quantities that are similar to helicity, very similar, called, for example, magnetic helicity, cross helicity, etc., etc. I won't talk about those, but I will. It depends on how slow I will be. Anyway, my plan is also to give a hint at the demonstration of the conservation of kinetic helicity because it's so new and involves localized fields, i.e. vorticity, vortex lines in tubes. Okay. We were here 1960s, and then I said something about the 60s before, and about topology, etc., etc., and we deroute from classical, say, fluid mechanics towards topology from helicity onwards. So tomorrow, okay? Right. Okay. So let me say something about these Helmholtz conservation laws and vortex dynamics, conservation laws. But well, you know, I encourage you, I will say something bad, especially on record, I encourage you to, on time to time, to take whatever you like in science and go deep as an historian, but with your mind as a mathematician. Because you discover many things that historians somehow miss or misinterpret. For example, they could say that Renzo, well, I'm not so famous, but Renzo was very keen on these kind of T-shirts, and it's not true. It's just that it's terribly hot and we are near the beach, and I like it. But I don't go around like this all the times. Okay, so be careful. Go yourself on stuff and check. So tomorrow, or better on Thursday, I'll say something about LIA as well, along the lines of being curious about the origin of certain things. Anyway, okay. So Helmholtz did many things, and I don't want to tell you what I think, how he got involved in that. Certainly was very keen on sound emission, and he was many times asked to check the organs cans and the production of sound. Maybe vortex rings had a role in that. We don't know. Okay, so I'm not going to show this derivation, but we have a master equation. This is Lagrangian derivative of omega over rho. I will mention rho very rarely because I assume that incompressibility is kind of important in what I'm saying. But you can consider also density, fluid density there, having a role, and this is just the standard omega grad U equation, okay? Oops. Right. So this, you know, okay, you have, of course, the Eulerian form of this equation, and d omega dt as the curl of U cross omega. And Emmanuel probably work on this equation every day. It's called Faradays Equation for magnetic fields, okay? Remember, take the liberty to, again, deroute. I will do it. I'm sorry, I have many, you know, I'm not so nice sometimes. Remember that this equation is highly nonlinear because there is a relationship between U and omega, whereas if you read out omega as a magnetic field, then you may think that the magnetic field is transported by U, is not related to U. Okay, so in that sense is simpler, let's say. Okay, so we have Faraday's equation, or Helmholtz and the conservation laws that are linked to this derivation by Helmholtz can be stated in this fashion. We have this paper, Helmholtz, a fantastic paper, 1858. I can't remember, maybe 60 pages, 50 pages, a long paper even. And let's say that in an ideal fluid, in an ideal Euler, ideal fluid, perfectly envisaged, vortex motion is governed by the following equation, by the following conservation laws. Okay, we have three laws, you may remember. One is irrotational fluid particles at time, initial time, at time, say t equals 0, remain irrotational at any subsequent time. Okay. Okay. Irrotational motion remain irrotational. And then the second law is a vortex line, in modern words, a vortex line, say L or something, is a material line, made by the same particles same rotational particles. I want to stress that. Rotational particles for all times. I want to stop there and I want to pause there. I said there are three laws. It's amazing that, when science is written, you read science, but then maybe 100 years later, if you read it again, you may give a different meaning to exactly the same words. So in books, this is stated and then is proved, etc. But in modern fashion, this is an amazing, this is a theorem that states quality, not quantity, states a qualitative aspect. And now it's very easy to reinterpret this as, okay, there is a region, say a vortex line, there is a region where vorticity is present, and the region, this one, where no vorticity is present. And the two regions, remember, do not mix. So this is a statement, and this is a statement about the complement space, or the other way around, if you like it. It's something that we don't know if Kelvin had this idea, but certainly is a topological statement. This is a topological statement, nothing else. We don't have any quantitative information about these statements, except proving that something that has vorticity stays rotational and something that is irrotational stays irrotational. And then the third law is quantitative in character, and it says that the flux, I'm sorry, I'm using flux. Okay, the strength of vorticity, through any portion of a vortex tube, is constant in time. Okay, so he was thinking of vortex tubes, so I needed to introduce a vortex tube. I'll do it in as quickly as possible, and vortex tube. Yes? Oh, it's a vector. It's a vector. Are you happier with an arrow on top, or just nothing at all, as Luis did, which is very economical and avoids these questions? I will underline things, and when I forget, please excuse me, but follow. Yes. Of course, it makes sense, and a beautiful question. And no, I won't do this. Not now. Of course, I will define helicity in terms of vorticity, yes. It's just a conserved quantity that was discovered much later, considering kinetic energy. That was my statement for the moment. No, I want to stress this. I mean, amazing. In the 1960 was found another quantity. Maybe there are others. Who says that the set is complete? But it's quite amazing. That's why I didn't want to move to definitions. It's just a quantity that was introduced and proven to be conserved in the 60s. Okay, so, you know, I have to talk about the vortex lines and all that. I will be extremely quickly, but I just, you know, you think of a line as this morning, and this line, imagine that this line closes on itself, maybe going to infinity, and we identify, as was said by Luis, the unit tangent. I put a hat, unit vector. Sorry, I'm old-fashioned. I studied in Cambridge, that's the problem. And okay, so this is a tangent, and you may think that the vorticity is proportional to some extent to unit tangent, okay? So, of course, there is a mod of vorticity. That means there is a constant in front of this. And then what you find in books is if, well, I won't spend time on this, but if you think of vorticity, for example, like omega 1, omega 2, omega 3 in R3, these are the three components of this vector, and the tangent similarly as a T1, T2, and T3, then what you have is that omega 1, you have tangent is dx ds. And so here you have to think of a dx1 equal to omega 2 dx2 and equal to omega 3 dx3, right? And then you do something terrible, is on record. You divide and multiply by ds, and you get the tangent here, and the components of the tangent that are proportional to vorticity. That's it. You have a field line, a vector field line. All right. So once we have these lines, well, the idea is just to combine them together. For example, to form bundles of these lines, you know, bundles of these lines, and you refer to the center line of this bundle. Imagine that there is a cross-section here, and there's a cross-section here and there, and you have a vortex tube. Vortex tube. So for a number of reasons, consistently with my plan in the lectures, I will consider vortex tubes of some finite thickness, of some thickness, and then LIA, you have to go in the limit, so to speak. All right, remember this morning, the point at a distance, and then you want to calculate the velocity at that point, and as the point approaches the center line, then you have eventually your Taylor expander LIA. Now, I want to consider thickness, and then I will consider particular cases where these vortex filaments are really thin. In other words, you can neglect cross-section. So the flux is just defined by the as you know, the vorticity through this cross-section, right? Vorticity through this cross-section. And you have the flux. The flux, I call it, flux circulation gamma, because by Stokes' theorem, you can relate that to the circulation, okay? Circulation around the tube, a simple loop around the tube. Okay, so we have done with that, and we're still at the time of Helmholtz, so nothing new. And so what we have is, this was the thing that struck Kelvin, in the fact that these vortices were permanent entities, as he says, in ether, in this ideal fluid, and the permanence was exactly the so-called mathematical character of these atoms, and he was very happy because finally he could prove that something was permanent and in time, and then we have this quantity, the flux of the circulation of vorticity through the section. Right. Okay. More or less at that time, Cauchy produced in a slightly modified way than I presented here, produce a proof that a vortex moving under the action of this diffeomorphism of this flow with very smooth, if it was in the shape of a knot, modern interpretation of Cauchy's work, this knot type, the topology of the knot, would be preserved by the flow. I already said the key words. The flow, I said, is a diffeomorphism. A diffeomorphism is smooth with derivatives. How can you think of a mechanism without viscosity that breaks the knot? There is no way to break the knot and rearrange it in a different way. And so just assuming that you deal with diffeomorphism, you should be just able to produce what Cauchy did. Well, the Cauchy work can be summarized in a kind of a lemma, if you like. I just erased these equations that I needed, but anyway, I will repeat. And Cauchy solutions to Helmholtz equations are formal solutions, not of great practical use, but the interpretation of the result is very interesting. So this is Cauchy, if you like, 18. I'm sorry, I'm not so precise with dates, but more or less, this is the reference. And again, we can say that in ideal, my wording, in ideal conditions, so under Euler equations, the vorticity is transported by the flow. Helmholtz is 1858. I quoted here 1815. It's impossible. He couldn't predict Helmholtz laws, right? But we can arrange these results in this fashion. It's transported by the flow according to this equation, omega rho. As I said, this is my own way to present this. Is this is what you call the Jacobian matrix, dx, with respect to the initial state. X0 is the position at the time t equals 0, and then multiplied by this omega over rho 0. And then actually he adds and this satisfies, as I said, forgive me for the business of the different dates, and this satisfies the vorticity transport equation. Of Helmholtz, the one I just erased it. Okay. Yeah. Okay, yeah, I'm going to do this. So you have vorticity at the initial position. Assume that rho is constant, much simpler. And then you have this Jacobian of the transformation from the initial position to the final position. But remember, at the beginning, in the decomposition of the flow, I assumed that there was also some deformation involved, UD. And so this means that you have, without any cuts or anything, you have just a change in the volume. The change in the volume may be squeezing the volume, rotating and stretching the volume, not changing the amount of volume, then is consistent with the idea of a diffeomorphism. Because diffeomorphism is just a map that is continuous and let's say, very smooth, differentiable everywhere in all spaces. So it's just the idea that if you have a smooth map by which you transport a structure in the fluid, then evidently the topology of this structure is preserved. And this is what you call ambient isotopy. So this doesn't add much to what I said of the deformation, because it's a deformation tensor. But at the time, in proving this, and you can prove it in one line by just assuming that you have a line element of vorticity, and then you do some little changing in time and space along the filament, you can prove this. This is just so easy. And then you can prove, and this is a little bit more of work, I don't want to spend time on this, that actually this satisfies the Helmholtz equation. It's a formal solution to the Helmholtz equation. So in other words, without maybe giving the emphasis I give to this result, Cauchy was saying, okay, you give me as an initial condition something that is a knot in space, k0, at time t0. So the fluid knot, remember, is a tube made of vortex lines and is your preferred knot or link. And it states that because of the action of this deformation tensor, you can deform it, of course. Geometry changes, but there is nothing that breaks the vortex line continuity. So it stays vertical, but it changes shape. So it can be mapped by this flow map phi that underlines this discussion to a knot k in time t greater than 0. So by proving that you have this result, and this result satisfies Helmholtz equation, then you are proving that, say, fluid knots, the flow map, your motion, the flow map, by the flow map, we can establish an equivalence class between fluid knots, between fluid knots and links. Okay? Remember, given a knot, a trefoil knot, you can deform it, it can get very complicated, but it stays knotted the same way. So this is really the background of what we may call topological vortex dynamics or topological field theory. This topological quantum field theory originates from classical field theory. Yes? Oh, no viscosity in this case, or no dissipation in more general context. No resistivity if you think of MHD, no viscosity in this case. Yeah, and it makes sense. By the way, I invite you to have a look. Maybe I'm wrong because age has its limits, many limits. And if I think on the first page of Helmholtz, really believe me, I didn't prepare this. I just go by hand, memory, etc. The first page, Helmholtz, 1858, he recognizes two problems. The problems of having vorticity, say, at a point, and as an initial step into this, because he said Euler, of course, knew that, or everybody knew about these vortices in water, etc. But he was like a devil thinking of a point with vorticity. How would be the velocity on that point? Would be infinite. So it's a devilish problem, he says. And then he says also, and of course I realize that all these approaches quite ideal, and there is a great problem that involves indeed viscosity, viscous flows. That problem is in the hands, my words, of Stokes. And I will tackle the first problem. Oh, very beautiful. He had such a clear view of everything. Okay, so now it's time to think about what I propose to do, an exercise together, because it encapsulates some basic calculations, very basic applied math, plus some not so basic thoughts. So that's why I'm proposing this exercise to you, and we do it together. Believe me, if you go to Kelvin's papers and you look for what I'm going to present you, you struggle. You struggle. I struggled. I spent so much time to understand what he meant exactly. Because first of all, there is no pictures. And secondly, everything he is doing is in his mind. He's following a plan in his mind. Okay? But you can check on the notes and on the paper. All right, so first step is this. We have our ether in this box, maybe a numerical box. And in this box, there are many of these very tiny filaments made of vorticity, and they are forming knots or links. I know it's not a joke. I gave seminars on time to time on this, and not exactly on this topic, but knots and links. And after maybe talking 1 hour, somebody comes to me, maybe an important professor. So don't be ashamed that you think I'm a student. I don't. And he says, Renzo, yeah, I followed, but I don't understand the difference between a knot and a link. Okay, so one way to keep it in mind is when you have one component, a tube that is knotted on itself, that is a knot. If you have two components, like I did before, Hopf link, or multiple components, that is called a link. That's it. Nothing else. Now imagine that in this volume there are lots of knots and links, and so he already was planning his vortex atom theory, and at a certain point he realized that, wow, if the two regions, the vortical region and the irrotational region, because of Helmholtz conservation laws, the first two conservation laws, do not mix, then I have maybe a problem with the potentials. With the potential, for example, the kinetic potential here. Why I'm worrying about that? I'm worrying about that because the genial Riemann, very young and not a student of Gauss, many people and many places you read that was a student of Gauss. Gauss had only one student, amazing, and is Listing, the person who introduced the word topology. By the way, if you want to look for a topology in Maxwell, go to the index and check for, don't look for topology, you don't find any. Go for geometry of position, because that was the word of the time. And then you find many entries. Wow, in Maxwell. Okay, and so Listing published a little book, and I studied German at school, and so I could read some. And is not so great book. It's a booklet on Möbius strips. Möbius strip was invented by Listing. And he was put in this little book. Why? Because he wanted to entertain people by cutting along the Möbius strip according to the number of twists. And in the evening, no TV, great times. The father was showing the kids, we do this. When we cut along the center line, we get something. When we cut along two parallel lines, we get something else, a knot or a link. And so kids were enjoying that. The book is very hard to find. There are only 3 or 4, and I got the copy in Geneva, visiting Geneva from Zurich. I think they have a copy. Anyway, so all right, so we are there, and Riemann Riemann, at a certain point, first paper of Riemann, 1857, out of his thesis, he conceived what we all know, or we should know, about the multiple connectedness of spaces. I'm using old words, by the way. So we have a region like this, you know, for example, the plane R2, and you can take a path, a closed path, i.e. a loop, and you can shrink it to a point continuously, right? And so if you can reduce the loop to a point continuously, that you call this space simply connected, and you may say that this space R2 is reducible. There are many equivalent definitions. But of course, if you have a hole in R2, let's say something like this, then an obstruction, then of course this loop can be reduced to a point, but this one cannot be reduced to a point, and the minimum length would be the measure of this circumference of the hole. Now, of course, if you think of a flow in a river with pillars from bridges, then that ideal two-dimensional flow, the surface is multiply connected. And this multiple connectedness now, with modern computers, etc., is getting back in many sports. In Formula One, for example, where the car is highly topologically highly complex, etc., etc. So people try to engage studies of this kind of flows, see what they can get. Now, if you take away these tubular knot, then you have a tube. You have an empty tube, okay? So in your mind, you do this operation, and at a certain point, you have a piece of empty tube. There is flow everywhere, all around, and so I'm looking at the complement, right? So you can transfer this situation that is impossible to draw it on the blackboard to this situation. He posed himself a problem to solve. And the problem is, okay, I consider a cylindrical geometry. Imagine that this cylinder is infinitely extended, okay? But I take it as cylindrical geometry for some reason that you will quickly realize. Then this is the axis. There is fluid everywhere except on the axis, better to say, except a tubular region centered on this axis, okay? So you have a tubular region here, and what this tubular region is empty represent? It represents this piece of a tubular region where you remove vorticity. Remember, the business is this flow and this flow, the vertical flow and the rotational flow, don't talk to each other. They do not mix. Do not mix. In superfluids, something like this. In condensed matter physics, defects, nodal lines, and tubular region. Okay, right, that's why I'm telling you this. Okay, so this is the geometrical setup. And then you want to explore this situation. So in order to explore this situation, having probably, I don't know, but having probably read Riemann, because in Helmholtz's paper there is a footnote. I told you, if you paid attention, I said there is a footnote to Riemann, and Helmholtz pointed out that when the ambient space, say, is multiply connected, maybe there is a problem. Now, problem with potentials. Potentials are no longer single valued if there is a hole there, are multiple valued. Why? Oh, this is amazing. You know, we teach mathematics. You teach mathematics, all of you, maybe to students of high school, etc. And then, I don't know, maybe you want to talk about the sine function. And then at a certain point, you say that the sine function, you reduce the sine function to 0 and 2 pi. you reduce it to avoid, oh, you can reduce it further if you want the functions to be invertible, etc., etc. When you say that we keep 0, 2 pi as a reference, we are using cuts. We are using cuts. We do not want the multiplicity to come into play, so we avoid all this. Without knowing, we use cuts. Cuts from Riemann. In order to reduce a multiple-valued function to a single-valued function. All right, so this is the geometrical setup of Kelvin. And then he says, OK, I can define a velocity field, u, in many ways. In many ways, he gives an example. It's just an example. In the most general way, I can define it, well, not in Kelvin's mind. This general way was just to use two potentials, something like this, phi and psi. These are two potentials, right? Of course, we can think of phi equal 1 and have the kinetic potential. The kinetic potential in books. No need to have an extra potential here. There is a reason why he uses two potentials, and is a beautiful reason, is a way to investigate a problem, okay? So we learn something there too. Okay, well, suppose for simplicity, suppose that phi is equal to 1, then if I think of this geometry, suppose that this is R0, I take a cylindrical geometry, this is I call it R1 probably, or something like that. I don't remember. I will see in my notes. And OK. If phi is equal to 1, we have the standard u equal grad psi. And then he immediately want to address the problem of multiple values for the potential. And so he says, what about if we take a potential like this? Psi, a particular psi, now I'm going to confuse you a little bit. The psi that he chooses is actually, in cylindrical coordinates, is actually the theta angle. The theta angle. It would be grad theta. I'm tempted, you know, I have a bad habit. I'm tempted to tell you, well, what about, do you know condensed matter physics? And this is the action, psi, and grad psi, grad s, or grad theta. Oh, we might mention something like that at the very end. But anyway, so this is kinetic potential. We take this potential, tan minus 1 of y over x. This is the potential. In the case, the simple case, we can work out derivatives, the psi in dx, and then, well, okay, you can do that, and this, and then realizing that your flow, according to this choice, your flow can be written, and because of the symmetry of the problem, yes, is a two-dimensional flow in actual fact, and is given by well-known minus y over x squared plus y squared and x over x squared plus y squared. We saw something similar in Professor Vega's lecture, you know, a straight vortex with a velocity, and he asked you maybe this evening to work out the velocity there is related to this. There is no, remember, empty tube in this case. And then you can show that the Laplace of this potential is 0, so it's an harmonic field. It's an harmonic field in the domain. And by the way, this is solenoidal and irrotational field, okay, field, U. Okay, harmonic field. Remember at the beginning of the Helmholtz decomposition, there was an harmonic field plus deformation field plus rotational field. Okay, so this is the psi function. There is no rotation here. Okay, no rotation here, and that's the situation. Now, let's forget about this instance, and we consider the divergence theorem. And by the divergence theorem, the Gauss theorem has many, many names. Actually, please remember the divergence theorem can be derived, now that we know, from Leibniz rule, okay? Because he parallels a volume integral with a boundary of the volume. And this is Leibniz rule. When you integrate a function, you know, you consider the limit outside the integration. And so you have, when you consider the divergence theorem, let me go back because I wrote something here that I don't want to forget. Okay, so this is the theorem, of course, is divergence of, let's take u, the velocity, okay? Divergence of u in dv, and this is just the flux of u in ds, where s underlined is S, first of all, S is just the boundary of my volume, and then when I use the underline thing is the surface of the boundary along, considering a normal pointing, say outwardly, this region, okay? So suppose that the region is finite as a cylindrical region, then the normal would be something like this, a unit normal hat. Okay, so this is the point. ds is like that. Right, so this is divergence theorem, and now we want to plug, and now plug in your velocity field u in this fashion, phi grad psi. So you do your work, and what you get is Green's first identity. That's it. It's always like this in the maths and science. You struggle 50 years, and then you can reproduce the result. You know, the noise goes away and it settles, and then you can, in a few lines, come up with this. So you do this, and from here and here, you get the following. Well, you know, the integral. So we have a volume equal to the surface. So we have a grad phi dot grad psi and plus phi Laplacian of psi. All this is in dv, and then this is equal to the phi times the new derivatives along on the surface ds. Okay, so this is Green's first identity. And fine. Now, phi and psi, remember that phi and psi are potentials. Oh, in this particular case, kinetic potential. Phi and psi are potentials. Scalar, if you like, a scalar function, of course, and they are called potentials. And now the question is, if you take a cross section here, a cross section, remember what I just draw the plane section. In the cross section you have a hole. So from Riemann you know that a potential is not well defined because it has multiple values. You can go round many times in this loop to get multiple values of the initial line integral. It's exactly as you do with sine, cosines, etc. Well, I can disclose the strategy. He reads Riemann, and Riemann says, well, we can insert cuts. We can insert cuts. How he does this? Oh, very simple. We have our obstruction, our hole, let's say something like this, and then he inserts cuts like this. Okay? So this is a cut, and then, please, it's just imagination, it's not a real thing, but with this cut, imagine that you can open up, let's do this, you can open up this you can, you can open up this, this domain, okay? Something like this. You do a cut, and then you open it up. And at this point, everything here is reducible. All loops are reducible, so the surface becomes simply connected. And this is what you teach at school, etc., at university, etc. But I was very surprised many years ago, because in Riemann doesn't care. I mean, it gives the concept. You use cuts, that's all. But Kelvin wanted to apply this idea. So when you push yourself to application, you always discover something new, always. And when you apply the idea, it becomes clear that the boundary that you have of the original boundary of this square gets changed by these two sides of the cut. I'm just on purpose emphasizing that I open up the surface so that evidently there is a cut Q, but this cut Q reveals a Q plus and a Q minus as additional contribution to the boundary. Okay, so this is something amazing that he noticed. Okay, now you know it, and just pretend that you don't know it, but you already have an idea where I'm going. Why? Because now he wants to put at work all this Green's theorem. So the Green's theorem is like that, and then he says, well, there is an equivalent form of this, which I write it here, and this, as I said, is an alternative equivalent form, and is this, no changes in dV. I'm sorry, I'm just... yes, I want to, it's a good idea to change a little bit of stuff. So I leave it here. Forgive me, I keep going like this. And then is a minus psi. I swap phi and psi. Phi plus the integral of psi, the normal derivative along nu of phi in ds. And this form will be, of course, this is a dv, this is a dv, and change sign, minus phi of this, integral in dv. Am I consistent? Maybe yes. There is a dv minus a dv on this side, and then ds here with a phi here. Or alternatively, I can write it like this. Okay, this is identical, but you see I swapped phi and psi, and so I have here psi, and then psi. Yeah. Pardon me? This one. Oh, sorry. Yes, there is a minus and there is a plus, because it's on the other side. Okay? Is that correct? Please tell me. Maybe I'm, you all know this. So when you teach, you always think the next step. And so you are a little bit superficial in the moment you write. I'm sorry for this. Please tell me if there is anything wrong. I'd like to correct it. Okay, and right. What's the difference? Well, apparently none. It's just the way the role of phi and psi play in this rewriting. Well, he says, okay, let's consider a case. Suppose, how to say it? I don't want to mix you up. I want to follow my notes. Clearly, if psi, as it is in our exercise, is multivalued, remember, is multivalued, is defined by tan minus 1, etc. If it is multivalued, then, well, when you take the gradients, multivaluedness means plus a constant, say. So when you take gradients, the constant disappears. So there is no problem here and there. And, well, here, second derivative of psi, so no problem. And here, no problem at all, because, again, there is a derivative. But here, yes, but here if psi is multivalued, then, as is in our case, then there is no guarantee that this equality is satisfied. Because when you plug in the values for psi, you don't know which multiple value to take into account. Yeah, you can say I set it to 0, but it would be a mistake. It would be a mistake. It would be something wrong. Well, he wants to prove this, which is amazing. So this is the bit of exercise we do together. To prove it. To prove it. Oh, it's so nice. Well, of course, it's been digested, and so I will be quick. So he works out all these contributions in this particular case. And so these contributions go like this. So let's start. Consider phi. We consider this case first and see if it is satisfied. When I say, applied mathematics, you put your hands on and you want to prove it, that is satisfied in a particular case. People don't like this attitude now. They want immediately to generalize to all sorts of, so we lose also information. Anyway, okay, so he says, okay, let's start to work out this quantity. I'm going to work out all these quantities maybe in a quick way. You can reproduce this on your own. And so it says, okay, I want to work out this quantity first. So it's just the new derivative of psi, but because of well, he doesn't go into details as I do with you. That's why the reading of his work is very hard. Anyway, you can use your cylindrical coordinate here, and it means that you have an ER along this direction and E theta along the azimuthal direction, and then Z doesn't play any role because of symmetry, right? So this new derivative is, remember, nu is normal to the surface of this cylinder, and so you have, maybe I forgot to say something about this, but I presume is okay, somewhere, anyway. And, okay, you work out this quantity, and this quantity is E hat R is exactly the radial unit vector that I mentioned before. You want to work out this quantity, and this quantity, I just explicit it out for you, is ddr of ER. I'm just expliciting this operator for you, plus 1 over R, dd theta E theta, plus, I said that there is no role for Z, but anyway, here you have it, Ez, and then this, you want it to work on theta, because I identify psi with theta, remember, and psi, remember, is arctan, tan minus 1 of y over x, so there is a theta involved, and all this has to be along ER, okay, dot ER. So when you do your calculations, you find 1 over R and E theta dot ER, and this is 0. Okay, so this term vanishes. Okay, this term vanishes. Then he goes on considering this case. Okay, let's work out this case. Okay, so this is 0, right? We just said that this is 0 in this particular case. So we have this integral. Let's call this quantity I1, and so I1, this integral, is just grad phi, grad psi, dv. No need for brackets, of course. And, okay, in Cartesian coordinates, just for you to check, is x dy of phi minus y dx of phi. and this is divided by x squared plus y squared, and this is in dx, dy, dz. Right. So when you reduce this expression in cylindrical coordinates, you get that is equivalent to 1 over, well, you see it, 1 over r squared d phi d theta. When you plug it in, there you have I1 equal integral 1 over r squared d phi d theta, sorry, d phi d theta in dr or d theta, your volume element, and dz. So you do your computations 0 and 1 if these are z equals 0 and these z equal 1, and then okay, we are here. You have a dz, and then the integral from r0 to r1 of 1 over r in dr, and then oh, I'm sorry, there is something. I cannot cross this. This is the organizer gave me many limits in life, and this is times 0 to 2 pi, and d phi over d theta in d theta, and so this is 0. Okay, so this is also 0. Okay. So this is 0, and then what about this? Well, we said it. I said it already, remember. I said the psi, because of the choice I've made, is harmonic. Laplace of psi is 0, solenoidal and irrotational. So also this is 0, because of assumptions, if you like. Well, I don't like to say assumption, because of hypothesis on psi. Okay? So this is satisfied. Happy man. He says, everything is fine. So now I go working on this part. And that is the part that interests us. Okay, so let's see how he does that quickly. So he put at work Riemann's. He put at work Riemann's idea of what we may call Riemannian cuts. So he says, okay, I have to cut the domain to reduce the multiply connected domain to a simply connected domain, and oops, too much. And in order to do that, a cut. You know, a cut in 2D, a cut is something like this, right? Here is a virtual 3D, is actually 2D, but okay, so I put a cut, and the cut is simply something like this, and then goes like down, and then like down, like this. So this is my cut surface. Okay, this is my cut surface. We call it, I don't know, maybe, I don't know, sigma as a cut. The surface sigma is a cut surface. Right. So this is 0, right? So this is 0. Remember here we had the Laplace of in dV, in the volume. No change in the volume. The cut does not change the volume. It's a virtual cut. It's a geometric cut. It's not a real cut. So it has to affect this. This is a surface integral. And because it's a surface integral, I told you, well, it's not explicited in Kelvin. That's the little work you have to do, but in his mind, the boundary of the volume changes. Because the boundary now is this cylindrical surface, if you like, bottom and top, just for being practical, and this cut. But this cut, not in Kelvin's words, but this cut has two sides. There is, of course, a sigma plus, and then there is a sigma minus. Q plus and Q minus for the cut. And we have a surface, so there are two sides. There are two sides, and we have a flow going around like this, remember. That is irrotational. And so the flow goes through this surface. And probably it bears some consequences. So, of course, he says, well, there is no guarantee, no longer the term, here we have a 0, remember the dV, and here I plug now psi, remember, psi. So I have a minus tan minus 1 y over x in Laplace of phi in dV, plus the integral, and this is a surface integral, and this is a volume integral. The surface integral is tan minus 1 y over x in the new derivative of phi in ds. And he says, well, this quantity that should be, this relation that should be satisfied, we cannot say in principle that is true, because we don't know which value to give to tan minus 1. Right, so he says, okay, if we put a cut, then we reduce the topology of the domain to simply connected one, and because it's simply connected, then tan minus 1 is well defined and everywhere, and so we can do that. But the problem is that we are going to modify S, because with the cut we have a sigma minus, a sigma plus. To tell you a long story short, I'll just show you the result. So he says, well, of course, the new surface, new boundary, let's say, is misleading, but yeah, a boundary, why not? The new boundary is just the old boundary, S, and then there is a sigma minus and sigma plus. Okay, yeah. I'm also checking my notes if there are mistakes, so that's why I pause on time to time. And then, okay, and then we can do the work, because now we have to compute this tan minus 1, which is theta, on this side and on the other side. And we can choose maybe a cut surface position that we like, that is most convenient. Maybe, I don't know, this is the Z axis, and this is the x-axis, and this is the y-axis, and I can take it in the xz plane, so that the normal to this cut surface is along the y direction, to simplify calculations. So if you do this, you will find that, okay, then if you compute this on one side, say negative side, then you can prove that it's 0 and the other is 2 pi. So you can adjust this. And okay, so remember, I'm sorry, I'm lost track of what I'm doing. You can reduce the original, I want to go back here. Oh yes, that's okay. So, okay, we are here. So you have to amend this S integral into this, oh, let me leave it like that. And then you have this plus, and then you have the additional sigma contribution. And because you consider one side and the other, you can easily see, certainly from the notes, that you have a 2 pi contribution when this theta comes out at one side and the other side, and then you're left with this quantity, which I write, having chosen this surface in the xz plane, I have the unit vector now j, the unit vector j that places the role of this nu of phi calculated up y equals 0, and this is dx dz because it's a surface integral, and he can show you that this is 0. Right. Can we summarize this? Yes, we can, and we can do the following. Let me state it in honor to Kelvin. Let me state it as a lemma by Kelvin. I generalize this lemma for the purpose of the following lectures, because it will come up again in a modern form in papers, as I mentioned, published only a few years ago. So I'll state it as a lemma, and the lemma can be written like this, lemma of Kelvin. I want to give you an exact date for this, 1869, and you can check is section 57 onwards. We can say this, of course, is our words, our modern way to express things, a multiply connected, well, we may say compact, closed manifold M. Let me use this number of Betty. You know, the number of holes you have in a manifold. Let's say that is the lowest order of Betty numbers. So it counts the number of holes. So of Betty number G, volume V, let's say, and surface S being the boundary, is reduced to simple connectivity. By the insertion of G cuts. For those of you who did topology, of course, on purpose I'm using these words, but you can reinterpret these words in terms of homological cycles and all that. Anyway, of G cuts, cut surfaces, sigma I, where this I goes from 1 to G, the number of holes, so that the Green's first identity for the multi-valued psi potential of the field U given by phi grad psi in M is given by this formula. You have on the volume side, the standard thing is grad psi grad phi plus psi Laplacian of phi in dV, and this is equal to the psi normal derivative along nu to the surface S of phi S, plus we have several holes, so we have to cut many times according to the number of holes, and so we have a plus sum of I goes from 1 to the number of holes G of kappa I, where kappa I plays interpret this as circulatory constant kappa. Remember, I told you that if you have an obstruction and you have a loop around this obstruction, then you can just shrink it, but not to a point. And this is this constant, the constant that measures the presence of these holes. So you have a number of circulatory constants for each hole times the flux of the potential phi through these cuts sigma I. Okay, where, as I said, where each kappa I denotes circulatory constant around the hole associated with sigma I, with the cut. Okay? It's, for the moment, I told you, please just accept this part as relevant to what I'm going to tell you later. Of course, you don't see the connection. Of course, you cannot see the connection, except the context I presented you. But there is a hint. You know, you have number of holes. So you have, this is a flux. This is a flux through the cut surface. So the flux can be also interpreted in terms of circulation. So if you have, you know, your typical solid torus, a solid torus, you need to cut it through a cut surface in order to reduce complexity, and you have this flux, and this one is circulatory constant in this direction, the other one circulatory constant in that direction, if you interpret this flux as a circulation as well. And these are the cycles generating the homology of the ambient space. Thank you.